I want to welcome you to my lecture, and the focus today is going to be on the properties of least square estimator. The last time we met, the focus was on the method of least square estimator. And of course, when I talk about least square estimator, it's an estimator that we use, to estimate the parameter of linear regression model. Okay, so when we specify linear regression model, specifying linear regression model is to actually think that, or to assume a linear, a straight line relationship between two variables. Okay, so in the outline, of course, I'm going to focus on the properties of least square estimator. Like I said, let's get started. We actually want to characterize relationship between two variables. Maybe, for instance, I want to look at the connection between the numbers of days a sick patient spend in an hospital, okay, and income, okay. We may also want to look at the relationship between mother's height and daughter's height. We want to look at the relationship between, amount to spend on advertising and the revenue. You understand what I mean? Now, the whole thing is going to start, like I said, with an assumption. Statistician normally uh, start with an assumption of what the model is going to be. But I told you the other time, um, you know, a very good way to start is to generate what I call a scatter plot. A scatter plot is, a diagrammatical plotting of the dependent variable against independent variable. With that, you're actually going to have what I call a sense of the relationship between the variable. So if you take a look at this guy now, okay, the very first step is when I want to fit a linear regression model, whatever model, to characterize the relationship, I actually need to come out with the design of a parametric model. Coming now with the design of a parametric model is just to specify whatever model you believe that is going to be, okay? That is what we call G of S theta. For the case of linear regression, the theta now, okay, is actually going to be beta naught and the beta one. Okay, you're actually going to have two parameters. Okay, the beta naught, the beta one, of course, the other time the beta naught, I call that regression constant, and the beta one actually call that regression slope. Okay, so after have we come up with what the model is going to be, okay, the next thing we're going to do is to fit the model to the data. The essence of fitting a model to the data is, like you all know, we normally use model to depict reality. Okay, we use model to depict the physical world. So when we feed the model to the data, the essence of doing that is actually to obtain the optimal value of what parameter theta is going to be. And don't forget, I told you the parameter theta. Okay, don't forget, the linear regression, the specification is actually days, right? We want to figure out what is going to be beta naught, what is going to be beta one, and the approach that we're going to use is going to be called least square method, because that particular method put into consideration minimizing the sum of square error. The sum of square error is just like what I told you the other time. Okay, when you take a look at this dependent variable, we believe there is a total variation around the dependent variable, and of course the model. Okay, this model, okay, the deterministic part of a model, we explain, a certain part. We expect that to explain the largest percentage in the variation around the response, and there's always going to be a random component, okay, which is going to be the place of unexplained variation It is not all variation in the dependent variable that the model can explain. There's always going to be unexplained variation. And what we always want to make sure that we minimize, the unexplained variation. And you know what, no matter how we minimize the unexplained variation, of course, the error is not going to be equal to zero. And what I mean by the error here, okay, if I'm looking at the relationship between Y and S, okay, if X is amount, or let's say is amount spent advertising, okay, let's say is amount spent advertising, and Y is revenue. Okay, so let's say Y is actually revenue. Okay, now error is going to be some other factor that could affect revenue that we don't capture in our model. Okay, so we want to believe on average the effect of such factor that we don't capture. We expect if its effect to be negligible, and that was why in the first place we said the expected value of the error equal to zero. Expected value of the error equal to zero actually means on average, okay, we expect any other variable that could affect the dependent variable, okay, that we don't consider right now in our model should have a negligible effect. That's what we mean. Okay, so the method of least square will guarantee that, the sum of square error, which I call unexplained variation, will be minimized. And of course, the number three step is, okay, after deriving what is my beta naught and my beta one, the estimator for them, how am I so sure that they're actually going to give a reasonable value? Okay, and that was why I said we should have a way to quantify how accurate our estimate for theta is. Okay, and if you really want to do that, we need to investigate the properties of an estimator. I'm going to say that again. If I really want to know, if I care about, or how valid is my estimator, then we need to revisit what we call the properties of estimator. So the essence of, figuring out or investigating the properties of estimator is to be, to be able to, investigate how valid is the estimator. And of course, if you hear about the properties of estimator, we talk about, is he unbiased? That's number one that we need to show. Number two, does he have a minimum variance? The only way I can tell if it has a minimal variance is to four of us have a derivation about the expression for the variance. And I can also investigate the consistency. Okay, investigating the consistency is to see whether as sample size increases, does the variance of the estimator, does it converges to zero? That's what we mean by consistency. So right now, you remember the last time before we went for Thanksgiving, I've already walked you through, giving a linear regression model, okay, with assumptions on the error. Expected value of error equal to zero. I just explained the other time, and the variance of error is almost stochastic. Almost stochastic, it means the error has a constant variance. And of course, this guy was actually the sum of square error. The sum of square error here is what I call unexplained. Okay, it's like we're talking about total unexplained variation. Total unexplained variation. What we mean by that? What we mean by total unexplained variation, we're talking about the totality of the variation in the dependent variable that cannot be explained by the model. We're always going to have that. Model cannot explain everything. And that is the reason why we say model is not the same thing as reality. Okay, model is not the same as reality. Okay, model give an approximate reality because there's always going to be a loss of information. So the loss of information here in a linear regression model is actually the total unexplained variation. And what we want to do, the method of least square, we actually assume, okay, give me 1 second. So the method of least square, we actually assume an approach, that can minimize the sum of square error. You remember the other time, uh, you know, uh, when I was deriving uh, days, okay, before we went on the Thanksgiving break, okay. So before we went on the Thanksgiving break, or what we actually do is I actually walk you through how to derive, from the first principle. Okay, give me 1 second. Actually walk you through how to derive from the first principle, this guy. Okay, what do we differentiate? You remember the other time we differentiated the sum of square error with respect to beta naught, with respect to beta one. We set that to 0, and we solve for beta naught and beta one. Of course, we're actually borrowing an idea from mathematics, because in mathematics that's what we call principle of optimization. Okay, in the principle of optimization, you need to conduct what I call derivative, okay, with respect to the estimator, okay, and after that you set to 0, then we solve for that. Whatever we get is going to be called a least square estimator. Now we got a least square estimator now for beta naught and for beta one, okay. And I remember before we go on break, we investigated how good is an estimator. Okay, so if I want to investigate how good is this estimator, now what I'm going to do is, what is the expectation of the beta naught cap? What is the expectation of the beta one cap? Okay, now if you take a look at this now, you remember we did this before we went on break. I've been able to show that the expected value of a beta naught cap is beta naught, and the expected value of a beta one cap is beta one. Some of you may be wondering, what is the meaning of this in real life? Of course, if I give maybe 1,000 students an assignment to work on the same thing, maybe I actually ask you to go into United States population. Maybe I want to work on, or relationship between mother's height and the daughter's height. Okay, maybe I ask you guys to take like a sample size of 50, from a population. You're going to be choosing them randomly, right? Now, and I ask you to compute the beta naught and the beta one, using the formula here. Okay, using the formula here. If you do that, the value you're going to get for your beta naught will be different from your friend. Everybody is going to have a different value for beta naught and for beta one, even though you are working on the same team. And that is the reason why the beta naught cap and the beta one cap can be called random variable. They varies. Okay, and we expect the sampling distribution of that to be normal. And not only that, if the sampling distribution is normal because it varies, we believe that the mean of the beta naught cap is going to be beta naught. If the mean of the beta one cap is going to be beta one. So I showed this last week, okay, how the beta naught cap and the beta one cap, can be regarded as a non-biased estimator. Now, another thing we're going to do is we also need to obtain the variance. What is the variance of beta naught cap? This is the variance. What is the variance of beta one cap? And what is the covariance of beta one or beta naught cap and the beta one cap? So why do I need this expression? In the applied statistical world today, whether you are using any statistical software, okay, these are actually the formula that were programmed behind the scene. And because this is a theoretical class, I actually need to walk us through how they derive this particular formula without deriving the variance of beta no cap, beta one cap. We cannot move forward. Like there's no way we can actually conduct any statistical inference on the beta naught or on the beta one. When I say statistical inference, we may want to test hypothesis about beta naught. We may want to test hypothesis about beta one. We may want to construct a confidence interval about beta naught and the beta one, but without having variance of the beta naught, we cannot conduct hypothesis or test or construct confidence interval about that. So what I want to do now is to walk you through how do we derive this guy, how do we derive this guy, and how do we derive this guy. So I'm actually going to walk you through that now. Okay, now we're actually going to go a little bit mathematical. I just want to show you how we derive the variance of beta naught curve. Okay, now of course, the beta naught curve. Okay, so uh, give me 1 second. Take I receive. Okay, give me 1 second. So now, uh, the next thing I'm gonna do is what is a you know that the beta naught is actually this. The beta naught curve is y bar minus x bar beta 1 curve. We want to get the variance of that. Why? Because the beta naught curve is a random variable. I told you the other time. If 1,000 investigators should compute the beta naught curve, they use this formula here, they're actually going to get different results. Because of that, it becomes a random variable, and we needed to find the variance because it varies. Okay, so the next thing that I'm actually going to do, okay, now take a look at this. I'm taking the variance of the both side. Now, taking the variance of the both side now, y bar is the same thing as this. Y bar is summation y over n, right? Okay. Now, this guy is actually this guy. And of course, this guy is this side, is this guy. Don't forget, x is summation x minus x bar all squared. It's some square deviation around x. And you need to take a look at that. Now, the next thing we actually are going to do now is summation is here, summation is here. We can factorize that, right? Okay, this is the summation now, bringing summation out. I'm actually going to have, uh, bringing summation out, and there's another thing that is common. Summation is common to both sides. Y is also common to both sides. I can put the summation here, put the y here, and write the remaining expression here. So which means, when you factorize that, that's what you're going to have. Okay. Now, the moment you have that guy now, the next thing we actually going to do is we want to find the variance of that. The variance will replace the summation sign. So right now, and the variance is only going to attract y, because assumption in regression is that s is fixed. Okay. The only thing that is random is y. Y is random. Okay, the variance will attract that. And when the variance attracts that, anything inside the variance, the whole of this was actually inside the variance. If you remember, when I have the variance of 3y, it's going to be 3 squared variance of y. So which means this guy is a constant. By the time it's going to be coming out, it's going to be squared. That was why that guy is a squared. Okay. Now the next thing I'm actually going to do, I'm right here now, right? Now, if I'm right here now, I need you to pay attention to what you have inside here. What you have inside here, you need to remember from mathematics, when we have a minus b all squared. You remember when you have a minus b all squared, it's going to be a squared minus 2ab plus b squared, right? So a is like 1 over n is a, okay? And b, okay, b is actually x bar over x minus x bar. So if I apply this guy now, I'm actually going to find myself here. You see that? apply mathematical knowledge now. A minus B all squared, going to be A squared, minus 2AB plus B squared. Now, the moment you get to that now, the next thing we actually going to do is to, if you take a look at this summation now, okay, summation I start from 1 to n is the same thing as n. Okay, so I'm going to use it to multiply this guy. Which is going to be n over n squared is going to be this guy. So using it to, multiply all of that, okay, we actually using n, summation to multiply that. I'm actually going to have this guy here. Now, you're actually going to see here, summation turn to n, it will reduce this guy. Okay, and where there is x minus x bar, summation, I'm actually going to use, it's going to be summation that. And because there's x minus x bar square here, you actually see summation that. But in a situation where there is nothing like a variable, okay, where we have 1 over n, summation turn to n. Okay, that's what we're going to have. Now, having this guy now, there's an assumption about this. Sum of deviation is 0. Okay, remember that? Sum of deviation is actually 0. So the whole of this is going to be 0. That's why you have that. Okay, and don't forget, sum of x minus x bar squared is actually, x, x, x. Okay, so this guy is going to be x, x, x. And don't forget, there's a s squared here. Okay, so which means that is going to cancel one of that. And that's how we got this guy. And finally, when you simplify this guy now, you're going to find yourself here. And finally, we're going to get ourselves there. So the variance of beta naught cap is now sigma squared summation s squared divided by n SSS. So this is how the variance of beta naught cap is being derived. Now the next is, how do we derive the variance of beta 1? Okay, the variance of beta 1 cap. Now, if I want to find the variance of beta 1 cap, okay, don't forget the whole of this is actually the beta 1. You remember? I'm going to walk you back. Take a look at that. Now, this guy, that I can also write this as x minus x bar, just y, divided by x, xx, because don't forget, sxx is summation x minus x bar all squared. Okay, need to take a look at that. Now, the next thing I'm going to do, so that was why we got this guy here. Now, just like what I said the other time, the variance here is going to attract y, and every other thing is going to have a squared. And that was why you see this guy having a squared, this guy having a squared, and we have variance of y. Like I told you, variance is only going to attract y as a variable. Y is random. The dependent variable is random. Every other thing is going to be constant. And when that expression want to come out of the variance, it's actually going to be squared, right? It's going to be squared. And that was why we got this guy here. And don't forget that, this guy here is the same thing as XSX. And, here, it's like you're having 1 over x, xs squared. Okay, and this guy is another xx and the variance of y. Okay, so this guy is going to cancel one of that. So that's why you have this guy here. And what is the variance of y? It's sigma squared. The variance of y is sigma squared. Okay, so that is how we derive the variance of beta 1 cap to be called that. Now, the next thing I'm going to do is we also need to investigate the covariance, of beta 1 cap and beta 1 cap. What is the meaning of that? The meaning of that is to investigate whether beta 1 cap and beta 1 cap are independent or not. Independent means maybe they don't depend on each other, or do they depend on each other? Well, let me tell you this. If you go back here, you're actually going to see they depend, which means if I want to find beta naught cap, I need to have beta 1 cap first. But the only condition under which they don't depend, what if this is when x bar is 0. If x bar is 0, what is going to be your beta naught cap? Your beta naught cap is just going to be the mean of y. Okay? So we're actually going to have a condition. Okay? So what we expect is that they're actually going to depend, okay, if x bar is not equal to 0. But if x bar equal to 0, they're actually going to be independent. And how are you going to investigate for independence in statistics? You want to investigate for independence, you need to look at the covariance. When the covariance gives 0, then the two variables are independent. But when the covariance does not give 0, then the two variables are dependent. So that's exactly what we want to do. What we want to do here, trying to, investigating for that. Okay, so I want to investigate for that the covariance of this and this. What is my beta naught cap? Okay, my beta naught cap is actually what you see here. What is my beta 1 cap? My beta 1 cap is this guy here. Okay, don't forget, as my beta 1 cap. That's my beta 1 cap. Then I want to find the covariance of that. Now, finding the covariance of that, what I'm going to do now is I can actually rewrite the whole thing because I got a summation here. I got another summation here. I can actually write this, write the summation, bring it out because it's common to both sides. What is other thing that is common to both sides? This guy and this guy also common to both sides. And that was why you see me writing them out, like a factorizing them because they are common between this guy here and this guy here. And after breaking it out, so this guy is the remaining expression. And of course, the covariance where we attract y and y, I'm actually going to say, okay, yi, yj. Okay, and you know what? I'm actually going to say yi equal to yj. So I'm actually going to have the covariance of yi, and the covariance of yi is the same thing as the variance of y. When I'm looking at the covariation between variables that are the same, then it means I'm actually working on within variation. It's going to be variance of y. And don't forget the variance of y is sigma squared. Okay, so when that happen, when the variance of y is sigma squared, so the next thing that I'm actually going to do, okay, right now is simplifying, okay, what you have here. Okay, simplifying, what you have there, like you're actually going to have this guy now. And the moment you have that guy now, okay, and when you apply the summation on this guy, don't forget, I told you summation x minus x bar is equal to 0. That was why 0 times all of that. That was why this guy is 0. And not only that, okay, when you apply this summation on this guy, you remember summation x minus x bar all squared is going to be xs, right? Okay, so the guy is going to be SSS. Okay, now when it becomes SSS, that was why you get this guy and this guy. This guy is SSS. Then you're going to be left with just negative x bar. So negative x bar sigma square over then actually going to have that. So what have we done now? Anywhere in the world, that guy is an expression, okay, for the covariance of beta naught cap and the beta 1 cap. And I told you the essence of obtaining the covariance between two variables is to investigate whether they are independent. The question is, are they independent? Okay, now when the covariance is not equal to 0, if you take a look at this guy now, this guy is not equal to 0. When the covariance is not equal to 0, then it means they depend. And what is the only condition under which this expression can be 0? The condition under which the expression can be 0 is when this guy, x bar, is 0. And if x bar equal to 0, then we're going to have a situation where we're going to say, okay, you know what, this guy, the covariance of this guy is going to be equal to 0. And when that happens, then we're going to say the beta naught cap and the beta 1 cap are not, are actually dependent. It means they are independent. And that was why I actually have this remark. Okay, which means they are expected to be correlated unless x bar equal to 0. So, don't forget, when the covariance exists, correlation exists. When the covariance equal to 0, correlation will be equal to 0. Don't forget that the correlation is a ratio of the covariance, okay, to the product of the standard deviation of the respective variable. Okay, so far so good. Now, the next thing I want to talk about now is the estimate of the population variance. You remember in the other time that you know when we're only focusing on the random variable y, okay, we're able to show this guy in class. If I'm focusing on y, okay, if y bar is an estimate of the population mean, then the sample variance, this guy is an estimate of the population variance. We've already shown that in class, expected value of a sample variance equal to population variance. But you know what? Can we have a way to estimate uh, what is going to be a good estimator for the variance if in a situation where y is related to x? You remember the other time when we were using this guy to estimate the population variance. Okay, y was not depending on anything. But what about situation now where we are assuming a straight line relationship between y and x, where y is related? What is a better way, or what is a better estimator to obtain the population variance? Now, if you want to do that, all what you just need to do is, if I have a model, a simple linear regression model, and when I uh, estimate, like, y here is the actual observation, okay, actual observation, but y here is a predicted. That is why it has a cap, predicted, or predicted observation, okay? And you can see here, you got a beta naught and a beta 1, but here, beta naught cap and the beta 1 cap. And of course, uh, if I look at the distance between this is like the difference between actual observation y minus predicted. Of course, that is the error, right? Then we square that, okay? This is squaring that, and we sum it, which we call the sum of square error. Okay, I told you the other time, the sum of square error is actually unexplained variation. Okay, now if we want to estimate the variance, okay, in a situation where y is related to x, then we can actually go by way of a sum of square error. Now, I'm going to show you this guy now. So, which means, you know, uh, if I divide sum of square error by n minus 2, don't forget, this guy here is the sum of square error. If I divide that by n minus 2, I'm actually going to have s squared, that's going to be unbiased estimator for sigma squared. Why am I dividing by n minus 2? I'm dividing by n minus 2 because the general formula is supposed to be n minus k, where k is going to be the numbers of regression parameters. 2 hit there because beta naught and the beta 1, we got two parameters. Okay, so now let us now for first talk about the sum of square error. So talking about the sum of square error now, okay, now I'm going to find what is the expectation of the sum of square error. As you can see here, the sum of square error is actually this guy, and don't forget what is y cap. The y cap is beta naught cap plus beta 1 cap x. So wherever I see y cap, then I'm going to put this guy, that was why you see that guy. Okay, I just put that now. Now we're actually here now. What is the next thing we're gonna do? The next thing we're gonna do is, can we have a way to substitute for this guy? Beta not cap. Don't forget the other time, the beta not cap is actually, I'm gonna show you right now. Take a look at that, right? Anyway, I see beta not cap, I can put y bar minus x bar beta one cap. Now, and that was why, if you take a look at this guy, okay, you know, for this guy, then this guy can replace that guy. You see that? Okay, don't forget that I said beta naught cap is actually y bar minus beta 1 cap x bar. Okay, so take a look at that. Now, the moment I got that guy down, so I'm already here. Okay, what I need to do, there's a y here minus y bar. I can put that together. Then if I put that together now, I'm going to have this guy. I'm also going to have this guy. Don't forget, we got a beta 1 cap x bar, beta 1 cap x. So beta 1 cap is common. I can factorize. Okay, so if I put that into consideration, now I'm going to have this guy. Okay, now when I have that guy now, so we're already here. You see that? We're already here. Now we're actually going to use this approach again in mathematics, where a minus b all squared is going to be a squared minus 2ab plus b squared. So what is going to be my a here? My a is actually going to be summation y minus y bar, okay? And, my b is actually going to be beta 1 cap, x minus x bar. So if you apply this guy now, that is why you're going to have the whole of that. Take a look at that. So we're using that row in mathematics. Now the next thing we're going to do now is we needed to take expectation of all of that. Okay. Now taking expectation of that is going to be that. You can see the expectation outside. You're going to see expectation there, right? And here, of course, don't forget that this guy is the same thing as xxx, which is this guy here. Then expectation of this guy. Take a look at that. Okay, why is the expectation attracting beta 1? Because beta 1 cap is a random variable. Okay, now you can see the expectation here. Okay, expectation attract all of these because anything y is a random variable, anything beta 1 is a random variable, the same thing here. Okay, so the next thing we're going to do now, so this guy is this guy. Okay, and of course, when you take a look at this guy here, remember that beta 1 cap is summation y minus y bar x minus x bar divided by summation x minus x bar all squared. Okay, if I want to find this guy now, it's just going to be this times this, which is going to be beta 1 cap summation x minus x bar squared, which I can also rewrite as this, right? So if you take a look at that, if that guy multiplied beta 1 cap right now, it's going to be beta 1 cap squared, okay, because of this guy. Okay, that was how we actually got this guy. So the whole of this has been reduced to that. And of course, we still have this here intact. Now, what is the next thing to do? If you take a look at this guy, it's like having a minus 2 cookies plus 1 cookie. If you simplify that, I'm actually going to have this guy. Now, where we are now, expected value of sum of square error give us these two expressions. And what we want to do now is to, simplify this side and also to simplify this. Okay, so how are we going to simplify that? Let's first start with this. And the only simplification that I need here, okay, can I have a way to simplify this? Remember, if I have the variance of y is the same thing as expected value of y squared minus expected value of y all squared, then what is this guy going to be? Expected value of y squared is going to be variance of y plus expected value of y all squared. Now, right now, I want to get the expected value of beta 1 squared. So expected value of a beta 1 cap squared now is just going to be variance of beta 1 cap plus expected value of beta 1 cap or squared if I want to follow this. Now, because of that, okay, because of that, okay, take a look at that. I'm saying this is this, right? And if that is that, initially, the variance of beta 1 cap, we've derived that to be sigma square over SS. You remember? I'm going to show you, here, the variance of beta 1 cap is sigma square over SSS. You remember? Now, I'm recalling that for this. And what is the expected value? Share the this is like expectation of beta 1 cap or squared. What is the expected value of beta 1 cap? Is beta 1. So when I square that, that's going to be beta 1 squared. Okay, so we have succeeded now in getting this for this, so that when we are done, we're actually going to come and substitute that guy here. But let us hold on for a second. Let us also simplify this guy. Okay, so if I want to simplify this guy, I want to start now. Okay, so this guy is the same thing as this guy. Okay, if I have summation y minus y bar all squared. Okay, so if you expand that, it's going to be y squared 2y bar plus y bar squared. Okay, now if you simplify that guy, you're actually going to have this. If you go by the lower level statistics that we've done before, now multiply expectation by both sides. Expectation is going to chase summation away. So it's going to be summation expected value of y squared. And, it's going to chase anyway. It's going to be expectation of that. Okay, so right now, I need you to focus here on this one. Okay, now what is the expected value of y squared? Is this guy. Because remember, the variance of y is expected value of y squared minus expected value of y squared. So if I want to find this, it's going to be this plus that. Okay, now if the expected value of y squared is this, similarly, expected value of y bar squared is going to be that. You're just changing y for y bar. Okay, and after they getting that, what is the variance of y? Sigma squared. What is the variance of y bar? Sigma squared over n. That's from statistical theory. What is the expected value of y? Is the regression model. Okay, you remember expected value of y is beta naught plus beta 1x. Okay, what is the expected value of y bar? Expected value of y bar is going to be beta naught plus beta 1x bar, which is what you have here. The moment you have that guy now, all we just need to do is to simplify. Okay, in the simplification, this is going to multiply that. Summation is going to turn to n. So it's going to be n that. Then summation multiply this guy. That's why you see this guy. Okay, n multiply this guy. That was why you have this. Now n multiply this guy. That was how you have this guy. Now, if you simplify this guy and this guy, you have n sigma squared minus sigma squared. Okay, so when you try to factorize that now, it's going to be sigma squared into n minus 1. That was why you get this guy. Now, the next thing now is bringing this guy and this guy together. Okay, and n here is the same thing as summation. Don't forget. Okay, then I can factorize and bring a summation out. Then I write it this way. So when I write it that way, the beta naught here can cancel this one because of the negative here. So the beta naught will be eliminated. When the beta 1 is eliminated, we're only going to have beta 1x minus beta 1x bar. Okay, and of course you can factorize out, right? Okay, that was how you actually have this guy. So the moment you have that guy now, don't forget about the squared for all of them. Don't forget the squared. Now we have this guy now. And when we have this guy now, if I want to rewrite this guy, I can rewrite that as beta 1 summation x minus x bar squared And this guy, don't forget, is same thing as xx. So I'm gonna have that. That was how you have this guy here, the square here also affect the beta one. So that was how you have that. So finally, this guy or this guy, give me one, this guy has already been reduced to that. Now the next thing we're gonna do is we're gonna plug in this guy. In place of this guy, we're gonna plug in that guy in place. So if you go back to where we're coming, we're gonna substitute for this and substitute for that. So when we do that, okay, so when we do that moving forward now, okay, we're actually going to have this because you know why? We plug in this guy into this guy here, into this guy here, and of course, we also plug in the expectation of beta one squared that we got into that guy, and at the end of the day, we're actually going to have this guy. Now, when we have this guy, all what we need to do is to simplify. When this guy is going to cancel that guy, you're only going to have a sigma squared. So, when you take a look at it, it's going to be n minus 1 sigma squared, beta 1 squared, xxx minus sigma squared minus xxs beta 1 squared. So this cancel that. So I'm only going to be left with this, and I'm going to be left with n minus 1 or sigma squared minus sigma squared. So when you bring out sigma squared, you're going to be left with n minus 1 minus 1. So n minus 1 minus 1 is going to be n minus 2. Okay, so now expected value of sum square error now is n minus 2 sigma squared. Okay, and don't forget, the other time we said s square is sum square error over n minus 2. So, which means expected value of sum square error now over n minus 2 is going to be n minus 2 sigma squared over n minus 2. So this cancel that. So what do you have? So which now means expected value, and don't forget this guy is the sample size. I mean, is sample variance. That is going to be equal to that. So which is going to be the end of the proof. Okay, so that is the end of the proof. Now, which means what we're telling the world is if I want to estimate the variance, okay, if I want to estimate the variance, okay, in a situation where a random variable y is related to x, I'm actually going to use sum of square error divided by n minus 2. So, and we have several ways to compute sum of square error. The other time I said the sum of square error is summation y minus y cap or square, right? Okay, it can also be this, it can also be this, it can also be that. Don't forget, the xyy is summation y minus y bar all squared. Don't forget that. Okay, and the xy is summation x minus x bar y minus y bar. Don't forget that. And the xxx is summation x minus x bar all squared. Okay, I think I just show you all of that. Okay, this is where I'm going to start in my next class. In my next class, I'm going to talk about consistency. Okay, the consistency property of an estimator. I think the summary, the takeaway from, what we've done today is just to walk one through number one, how to derive the variance of, how to derive all of this, this is what we did today. How do we derive the variance of beta 1 cap? How do we derive the variance of beta 1 cap? And how do we also derive the covariance between, the beta 1 cap and the beta 1 cap? Because we want to investigate whether the beta 1 cap and the beta 1 cap are independent or not. And of course, I told you the other time, if I really want to investigate how good an estimator is, I also need the variances. Because if I was able to get the variance, of course, I will be able to investigate for efficiency. If I was able to get the variance, I will be able to investigate for consistency properly. And not only that, without the variance of the beta naught curve, beta 1 curve, there's no way we can conduct a statistical inference on the beta naught curve and on the beta 1 curve. So when I say statistical inference, there's no way we can test hypothesis about the beta naught and the beta 1, and there's no way we can actually construct a confidence interval about that. So now that we have the expression for the variances, the variance of beta naught curve, the variance of beta 1 curve, in the next lecture, we'll be able to investigate the consistency of an estimator. You remember what we did the other time? An estimator is said to be consistent if as limit n tends to infinity, the variance of the estimator can approach zero. Okay, so that is what we're going to do. We're going to investigate, okay, the next lecture, whether the beta naught curve, the beta 1 curve, whether they are consistent or not. And the only way to do that is to find the limit as n tends to infinity for their variances. Okay, this is where I'm actually gonna stop today. Okay, make sure you stay safe. I'm actually gonna meet we're gonna meet in class on Wednesday. Bye for now, everyone.